So thanks very much for the introduction. Thanks everybody for coming out. It's nice to be back in Atlantic, Canada, I guess at least a little bit virtually because I did my PhD at Dalhousie. I'm from PEI, so my whole life has been in Atlantic, Canada up until the last year and a half. So yeah, I picked a bad time to leave, but hopefully, we'll be back there again sometime. So as Danielle said, I'm going to talk about vertex critical graphs today. And specifically, we're going to look at families of graphs that have only finitely many of these vertex critical graphs. And this is joint work with Chin at Wilfrid Laurier and my current postdoc supervisor, Joe Sawada at the University of Guelph here. So there is one more person to thank for this talk, and that's my little baby boy, Asher, who was just born on August 8th. Because he kind of sped up the process for this research. Because it started, Chin came to visit me and Joe at the University of Guelph last October, so about a year ago. And we had some results, but then we realized one of the results we worked on was already proved. We found it kind of in a recent preprint, so we kind of got discouraged and left our other results for a while. And then COVID happened and we really the research hit the back burner. But then because my wife's due date was approaching and we knew I would be out of commission for research for a little while, we started to pick back up and we got some more results and we got the paper submitted. So a big thanks to my little boy Asher here. So there's a little bit of a connection here. I'm not just a proud dad bragging about how cute his son is. So, and if you hear a screaming infant in the background, that's where that's coming from. So back to the math. What are we actually going to talk about here? So here's the outline. We're going to do some brief definitions. Before we get into vertex critical graphs, we're going to talk about the K-coloring decision problem and a little bit of background on the computational complexity of that problem. Then we're going to move into how vertex critical graphs are related to that problem. Then we're going to look at two different families of graphs, showing that they have only a finite number of these vertex critical graphs. And then we'll get into some open problems. So that's kind of the outline. And again, this is a graph theory seminar, so I assume a lot of these definitions are okay for a lot of people. But just to make sure we're on the same page, in particular, the path here that I'm going to use, Pn, n is the number of vertices, so not the number of edges. Plus is going to denote disjoint union. Right, so not the join. I am, just kind of by convention in these graph coloring areas, most people use plus to denote disjoint union. I'm personally more of a fan of using union, but to be consistent with all this, we'll use plus for that. And one nice thing about that is that it's kind of intuitive to say if you have the disjoint union of L copies of a graph, you can just write that as L times G. So for example, this graph here is P2 plus 2P1. So here's our two P1s. Everything's good. Again, basic stuff, but just make sure we're all on the same page. And coloring is just a proper coloring, right? No fancier coloring than that. Adjacent vertices receive different colors. And another one that a graph is H-free if it doesn't contain H as an induced subgraph. So for example, this graph, our 5 cycle is P5 free because there's only one subset of 5 vertices and it does not induce a P5, but it's not P4 free, right? Because we have P4 here. Even though you can find a P4 in here, it's not in, or sorry, a P5 in here, it's not induced. So just wanted to make that clear. When we say H free, we mean no, H is not an induced subgraph. So a big definition here is for fixed K, right, we have this K coloring problem, which is to determine, given a graph, if it's K colorable, right? It's no more complicated than that. But solving this problem is very difficult. So we've known for a very long time that K coloring is NP complete. So it's a very hard problem for all K greater than or equal to 3. And even if we restrict the input graphs, we don't always get an improvement. So if we restrict the domain of what we're going to decide the K colorability of, if we're only looking at H-free graphs, where H contains a cycle, the problem is going to remain NP complete. So we can't forbid a single subgraph that contains a cycle and expect to reduce the complexity of this problem. The same thing if the graph H contains a claw. So if we want to limit the input graphs to claw-free graphs, we're not going to reduce the complexity here. So what we're left with then, if we want to try and make this a problem so that it's not NP complete for a certain family of graphs, and we only want to forbid a single induced subgraph, we're going to have to forbid an acyclic claw-free graph. So that gets us thinking about paths, right? We're going to have to forbid paths or the disjoint union of paths. So let's just start at the basics here. What happens if we forbid a P2? Well, nothing is interesting here. If you forbid a P2, you don't have any edges. So everything's one colorable and we can get an efficient coloring, no problem. If we forbid a P3, then the graph is a little bit more interesting, but not that much more so. Because we're just going to have that the graph is a disjoint union of cliques, and we can color that efficiently, right? So in these families, we don't have the problem, the K coloring problem can be solved efficiently for all K. P4 free, things get a little bit more interesting. A graph is P4, it's going to be a cograph, which we don't really need to worry about what it means, because that implies that it's a perfect graph. And we've known for a while here, an old result from the 80s is that we can color perfect graphs efficiently in polynomial time, but I mean by efficiently, for every value of K. So if we want to decide the K colorability of P4 free graphs, we can do that in polynomial time for any K. Okay, so the first two cases here were kind of trivial. P4 free, a little bit more was going on. But when we have PM free for some m greater than or equal to 5, it's not really clear what we should do. So these cases all kind of need to be handled on their own. So we'll just show some kind of negative results in here. So areas where we could not reduce the complexity. So if we try and forbid a P7 or a path longer than a P7, and we try and solve the K colorability problem for K greater than or equal to 4, that's going to be NP complete. This is a much more recent result. And in the same paper, it's also shown that if we want to forbid a path, so now we can forbid a path that's a little bit shorter, we can forbid a P6, and we want to decide K colorability for K greater than or equal to 5, it's going to remain NP complete. So we're really narrowing in the places here, right? Before this, all Ks were fair game, all Ms were fair game. We didn't know. Maybe you could forbid every path and get a polynomial time algorithm. So there is a positive result though. For coloring P6 free graphs can be solved in polynomial time. And this paper is a very impressive paper. A lot of work involved just to get this one case where we forbid P6 and we want to solve the for coloring problem. So this result was a big breakthrough because this was a remaining case for a long time. And 3 coloring, we're not really going to worry so much about 3 coloring and stuff, but you can solve that in polynomial time for P7 free graphs. So if you want to draw a little diagram for yourself, you kind of get the situation going in your head. But what we're going to focus on now is where we have even more positive results than this 4 coloring problem for P6 free graphs, right? Because what about P5? That's the one we skip right over here. Well, the nice thing about P5, it doesn't follow as quickly as perfect graphs did with the P4 free stuff. But if we wanted to solve the K coloring problem for P5 free graphs, we can solve this in polynomial time, and we can do that for every K, right? For any fixed K, we can get this. And this result was also Chin and Joe and a few other co-authors were on this. So just to kind of illustrate how this goes, right? We have our P5 free graph here, the cycle again. will take their nice elegant algorithm and represent it by this nice elegant rectangle. And the algorithm will chug away, and in polynomial time, it'll decide if it's 3-colorable, right? Why am I going through all this? This makes perfect sense to everybody. But there's another thing that their algorithm will do, is that if the graph is k-colorable, it will return a valid k-coloring, right? So this is a significant advantage of this algorithm, is not only does it say yes or no, if it decides that the answer is yes, then it will return a valid coloring, right? So here, the algorithm would also spit out this 3-colored graph. So this is what's known as a certificate to verify the output, right? So we do the algorithm, right? It's implemented in polynomial time. However, Chin and Zhou and their co-authors decided to do this. It says yes, but then it also returns this coloring of the graph. And this is actually very easy to verify. So if you want to double check, make sure you didn't make any mistakes in implementing the algorithm, you can check if this is actually a valid 3-coloring, and very quickly. So what about the other end of this? What if we take a graph that's not 3-colorable? What happens there? So let's take this graph, P5 free still, but it's not 3-colorable. This can be solved in polynomial time. But how can we verify this no answer? What can we return as a certificate that we can give to the user, and they can quickly verify that this graph is not 3-colorable? So this is the idea that gets us into kind of the main point of the talk. So let's just take this graph that's causing us problems. It was not 3-colorable. The algorithm told us that in polynomial time. And we're now looking for some kind of certificate to verify that answer. So what we're looking for is some kind of substructure that's hopefully as small as possible that prevents this graph from being 3-colorable. So we can kind of convince ourselves pretty easily, 3-colorable, we have a vertex of degree 2. We can probably get rid of that guy. Now we're left with this induced subgraph. Everything still requires 4 colors, but now you remove any vertex and we still require 3 colors, okay? So this graph is, and some of you might know this definition, is a 4-vertex critical graph. This is a complete graph on 4 vertices. And by that, we mean it is not 3-colorable, but every induced subgraph, so, or you remove any vertex and you will get a graph that's 3-colorable. So that's what we mean by a k-vertex critical graph. The nice thing about these k-vertex critical graphs, and this is not too hard to convince yourself of, is that every graph that's not k-colorable has to have a k+1 vertex critical graph as an induced subgraph. So these vertex critical graphs seem like good candidates for certificates to verify a no answer in our thing, because if we have a graph that's not k-colorable, it must have a k+1 vertex critical subgraph. Return a k+1 vertex critical subgraph, and that'll be smaller than your original graph, and we can see. The issue is it's still going to be difficult to verify that that is a k+1 vertex critical subgraph, because there's infinitely many of these vertex critical graphs, k-vertex critical graphs, for all k greater than or equal to 3. So it's actually not going to be quick to verify if this is indeed k-vertex critical. The other issue is just a minor technical issue for the talk. There's another notion of criticality where you remove any edge and you drop the chromatic number. We're not going to deal with that. So instead of just saying k-vertex critical all the time, we're just going to say k-critical for this talk. So anytime I say k-critical, you think vertex critical. Okay, but we resolved the second issue. The first issue will take a little bit more to resolve. But the idea here is maybe just like in the decision problem, if we restrict the input graphs, right? So do we maybe have families where there are not an infinite number of k-vertex critical graphs? Maybe there's only finitely many. And we turn back to our trusty family of P5 free graphs, and we get a result. Again, this one also has Zhou and Chin in it as well. And this one just kind of improved the result to take it from a polynomial time algorithm to a linear time algorithm. But the idea is, if you have a 4 critical P5 free graph, then you have to be one of these 12 graphs. So in general, there's infinitely many of these 4 critical graphs, but of those, there's only 12 that are P5 free. So this means that we can solve the 3 coloring problem for P5 free graphs in polynomial time and certify the answer, right? So in the yes answer, we use Zhou and Chin's other algorithm to return a coloring. Now that we have only finitely many of these, we can decide the colorability by searching through each of these graphs as an induced subgraph and returning it if we find one. Right, so just to illustrate that, this illustration will probably be a little bit more helpful than the other one. So this is how having only finitely many k+1 critical graphs gives you a polynomial time algorithm to solve k coloring. So let's take this graph here that is P5 free, and we want to decide if it's 3 colorable or not. So how we're going to implement this algorithm is we're just going to, scan. Is this graph an induced subgraph? So we're going to take all subsets of size 4 and, and n to the 4 times or whatever. No, that's not a subgraph. This one, no. This one, no, no, no. And we keep going on until, we either exhaust the list, we find that none of them are induced subgraphs, or in this case, we find that this 4 critical P5 free graph is an induced subgraph of this graph. So we can return no, this is not 3 colorable, and we can return this graph as a certificate. So then the user can take this graph and search through the 12 graphs themselves, the 12 4 critical graphs, and say, was this right? Yes, I see that now. So from this, we're able to get a fully certifying polynomial time algorithm in the cases where we have families of graphs with only finitely many k-critical graphs. So that was just 4 critical, right? And that was a long way to go. Are there any families of graphs where we have finitely many k-critical graphs for any k greater than or equal to 5? The answer is yes. So here's a table here. A lot of these are from P5 free graphs, and you forbid another graph. So C5, the banner, we don't really need to worry about what that is, or also forbid P5 complement. We get a bunch of these results. So there's finitely many 5 critical if you forbid P5 and C5, finitely many 6 critical if you forbid P5 and a banner. This result is interesting. There's finitely many k critical for all k if we forbid P5 and its complement. So this is kind of nice because now we can solve the k coloring problem in polynomial time and certify our output for all k in this family of graphs if we forbid P5 and P5 complement. And then there's some other stuff going on. We have another all k result. This result by Kathy Cameron is also at Wilfrid Laurier, and some other co-authors we'll come back to later. But for now, we can just note that. But there's one other thing to note about this is when we get to higher critical numbers, we can't always get a complete list. So only these values highlighted in blue are values where we have the complete list of all of these critical graphs. So like we had before, we had the 12 4 critical P5 free graphs. Here we have a complete list. Here we have a complete list. But the other ones, the proof is just existential, that there exists finitely many of these. So without that complete list, you actually can't implement these algorithms. It's nice to know that, a polynomial time certifying algorithm exists, but it actually cannot be implemented unless you have that complete list of the critical graphs. So that's one thing to note, that sometimes here we don't get, we don't have a constructive proof that there's finitely many, just an existential. So one of our results is going to be existential, and then one of our other results, once we get to it, is going to be taking that one of these known families and actually generating the complete list. But before we get there, let's just think about what families what graphs, just like we did with the K-coloring problem, what graphs H can we forbid and hope to get finitely many K-critical graphs for some K, right? So just in case in the back of somebody's mind, they've been thinking, okay, the K-coloring problem is NP complete. If we have finitely many K+1 critical graphs, we have a polynomial time algorithm, and we can't forbid a cycle or a claw and hope to get a polynomial or hope to reduce the complexity. Maybe you're trying to scheme out a little P equals NP proof. Well, you're not going to be able to do it with those two families because these are separate, right? Even if P does equal NP, there's still not going to be a finite number of H-free graphs if H contains a cycle, or H-free graphs if H contains a claw. So for all K greater than or equal to 3, there's still infinitely many of these critical graphs. So we didn't really expect this here. This is just kind of a technical point. But here is a graph that causes some issues. So if H contains 2p2, so just 2 disjoint edges, nothing between them, that's very restrictive. So if we forbid 2p2, there's still an infinite number of K-critical H-free graphs for all K greater than or equal to 5. So any graph H that contains 2p2 is going to have infinitely many of these K-critical graphs. So for example, P5 contains 2p2. So even though there was a finite number of 4 critical P5 free graphs, there's going to be an infinite number for all K greater than or equal to 5. So that's a bit of bad news. But here's some good news, that the world of where this could live, it keeps shrinking and shrinking. So a very recent result is that there's a finite number of 4 critical H-free graphs, if and only if H is an induced subgraph of one of these 3 graphs. And the last graph really there's really not 3 graphs here. There's really infinitely many because P4, this L can take on any value. So we can have P4 and the disjoint union with any size independent set. And we're going to get finitely many H-free graphs, finitely many 4 critical graphs in every case there. So the 4 critical problem here is completely solved, which single subgraphs we can forbid as an induced subgraph and get a finite number of these 4 critical graphs. What this leaves open, though, is for larger values of K, right? Which graphs H can we forbid as an induced subgraph and get only finitely many K critical graphs for values of K greater than or equal to 4? Why don't we go all the way and think about for all K, right? Because that was kind of my favorite result that I highlighted. Those 2 favorite results in the table were when we have a polynomial time algorithm or a finite list for all K, those are kind of the results that have the most weight. So can we answer this question? For which graphs H are there only finitely many K-critical H-free graphs for all H? So combining a few of the other results, H has to be one of these forms, right? It has to be an induced subgraph of P4 plus LP1. So it has to be one of these values for some L. The first case we can all convince ourselves right now. We'll go through this proof just very quickly, why there's a finite number, if you forbid LP1, why there's a finite number of these K-critical graphs for all K. Well, if we forbid LP1, we're essentially just restricting the independence number. We're saying the independence number has to be at most L minus 1. If it's K-critical, the clique number has to be at most K. So it's just Ramsey's theorem now, right? Because any graph over a certain order is going to, by Ramsey's theorem, either have an independent set bigger than we allow or a clique bigger than we allow. So this case is easy to solve. The remaining 3 cases do not follow as easily, right? So this is all that was open. What we're going to solve now is this case, P2 plus LP1. This is kind of the main contribution that me and Joe and Chin did, was show that there's a finite number of these graphs for all K-critical P2 plus LP1 free graphs for all K. So I'll just sketch the proof here, and then I'll explain kind of why I think this is a nice contribution to to the area. Right, so this is the theorem. There's a finite number of these. So the proof is inductive. So it's easy to show for small values because the only 3 critical graphs are odd cycles. And when we forbid this graph, we get a finite number. Very easy to show that. So we prove this by induction, and then we take our, so the inductive step is kind of proved like this. We take a graph G that's a K critical P2 plus LP1 free graph for some fixed L. And now we take a maximum independent set S in there, and we look at what must happen. So if we remove the maximum independent set S in a graph, we can forget about K critical for a second, but just this graph is K colorable. Its chromatic number is K. If we remove this independent set, the remaining graph has to be K minus 1 colorable, because if the chromatic number dropped more, then we could just add this back in and color everything with the same color, and we would be all set. And we would contradict that the chromatic number is actually K. So the important thing is the remaining graph here is K minus 1 colorable, which means it has to have a subgraph, an induced subgraph, G prime, that's K minus 1 critical. And now it's nice that we're doing this inductively because this graph still has to be P2 plus LP1 free. So we know something about this graph already, right? So what we can think about equivalent to showing that there's a finite number of K critical H-free graphs is to show that if you have a K critical H-free graph, it has to have finite order. So what we know about G prime is its order is bounded by a certain number that we won't talk about because the technical details are not that interesting. And then we just look at this. So if S is too small, we're done again by Ramsey's theorem, right? We can apply the exact same argument we did for the LP1 free graphs, and we can be done. And by too small, I mean this. If it's smaller than this, whatever G prime's maximum order is times L minus 1. If it's too small, we're done by Ramsey's theorem. And if it's too big, then we're going to force one of two things to happen. We're either going to force an induced P2 plus LP1 with a vertex in G prime and our maximum independent set, which is, explicitly forbidden. So that would be a contradiction. Or if that doesn't happen, then we necessarily have to have a vertex S in our maximum independent set that's adjacent to every vertex in G prime. So why this has to happen, there's kind of a technical lemma in the background that I left off, but this is the main idea of the proof. And why is this an issue? Well, G prime is a K minus 1 critical graph. We are joining a vertex to it, which makes the graph G prime joined with S a K critical graph, or even just K colorable, and that's a proper subgraph of the graph G, which is supposed to be K critical. So that's a contradiction, right? We can't have a proper subgraph, a proper induced subgraph of G that's K critical if G is supposed to be K critical. That contradicts just the definition of what it means to be K critical. And that's really the whole proof. And why this is nice, in my mind at least, is a lot of the other proofs, from the table to fill out, they're nice work, but what they usually do, their usual method is to apply the strong perfect graph theory and say, okay, if it's K critical and forbids a certain subgraph, we have to have a 5 cycle or the complement of a 7 cycle. And then you put that in the graph, you look at every possible vertex away from that. So is it adjacent to 2 vertices in the C7 bar, or 3 vertices, or all this? You go through all that casework and you show in each case, based on the structure of the graph, the order is bounded. So it's just a lot of casework, a lot of grunt work. And I think this inductive argument, the inductive application of Ramsey's theorem, will hopefully generalize to the other 2 cases. We haven't been able to do that yet. There will be more work involved, but at least has the potential to generalize, whereas the other cases are very specific to the subgraph you forbid. Okay, right? And so just as I said here, so now the only remaining subgraph, or the only remaining graphs that we could potentially forbid and hope to get a finite list of these k-critical graphs that isn't already known, we have to have these two forms, P3 plus LP1 or P4 plus MP1. It's known for L equals 1 and it's known for M equals 0. But for other ones, it's just completely wide open. But what our results did answer is this other bounded order problem. So if we want to know which graphs H of order 4, right? So we're really restricting this problem. We're really capping it off. There are only finitely many k-critical H-free graphs for all k. Then we kind of have a complete answer, because here are all the graphs, all non-isomorphic graphs of order 4. We can get rid of all the ones with a cycle, all the ones with a claw, which is just this guy, I guess. And then we just look at the ones that are just have paths as every component. A lot of these were known. This one just recently shown, infinite. P4 free, the only critical graph is the complete graph. The 2K2, I called 2P2 earlier, it's infinite. And P2 plus 2P1 is the one that wasn't known. That is just a special case of our result. So now that is finite. So that gives this dichotomy theorem, right? That if you have a graph containing at most 4 vertices, there's a finite number of k-critical H-free graphs, if and only if H is an induced subgraph of one of these 4 graphs. So that's kind of nice. It's not really the dichotomy we wanted. We wanted to remove this restriction on the order of the graph, but at least we got rid of one of these cases, and we do have this decided for graphs of fairly small order. As well, from that, with our restrictions on the structure of these graphs, as I mentioned before, right, we want a complete list of these k-critical graphs to implement the corresponding polynomial time certifying algorithms to solve the k-coloring decision problem. So we were able to use that to get a complete list of 4 critical P2 plus 2P1 free graphs. So we can actually implement a 3-coloring algorithm in polynomial time to solve this for this family of graphs by searching through these 9 graphs as subgraphs. So some of these appeared as P5 free graphs already. Some of them are different, and we have a smaller list in general. But for 5 critical and above, all we know is that there's a finite number of these. We don't know how to get them. We don't have a very good bound on the order either. So our result kind of falls into that category where, right, we show that they're finite, but our bound involves, if you trace through the details in our proof, right, it's a Ramsey number of a Ramsey number. So it's going to be a huge bound on the order. So it'd be very difficult to generate these for 5 critical and above just based on our result. So more work will probably be needed there. But another contribution we made is looked at this family. So if we forbid P3 plus P1, right? So this is in the recent paper of Kathy Cameron, right? So what they actually did was they looked at this dichotomy. They proved this dichotomy theorem. If you forbid P5 and another graph, so if you're looking at graphs with no induced P5 and no induced H, and H is a graph of order 4, then there's a finite list of these in every case except for if H is 2P2 or K3 plus P1. So part of their paper, they had to show that there's a finite number of k-critical P3 plus P1 free graphs for all k, right? Right, but like our result, there was no complete list of these given, right? So no algorithm that could be given. It was known for 4 critical, a complete list was known, but for k greater than or equal to 5, it wasn't known. Right, so we can't implement any of those k-coloring algorithms for any k greater than or equal to 4. Right, so we can only solve 3 coloring in polynomial time if we want to certify a no answer. Right, and 3 coloring is not very big. So here's another contribution that we did. And I really like this result because of how we proved it, because we were working on it for a while. And then Chin just kind of remembered this result from Olariu in 1988 that says G is PA-free if and only if each component of G is triangle-free or a complete multipartite. And, so I wasn't alive in 88, but Chin said this was his thought in 1988. This result will never be of interest to anyone, which is always nice to think about a paper, I guess. I'm assuming he wasn't the referee because it did get published. But here's the thing about the PA. We don't really need to, right? This is what the PA is. And it's actually equal to the complement of P3 plus P1. So 32 years ago, Chin said this result will never be of interest to anyone, so much so that it stuck in his head for 32 years that there was this paper out there with this result that was completely useless. And then we used it to prove, our theorem for this. So from this, you do the complements and you can impose a lot more structure on the P3 plus P1 free graphs, right? So if you're thinking about a critical one, we get a lot of structure. So now, not only do we know they're finite, but we actually get a pretty tight, or we get a tight bound on the order. This bound is tight, right? There are k-critical P3 plus P1 free graphs that have order 2k minus 1. Just think about the complement of an odd cycle. That's what we're getting here. And also, these graphs have to have independence number at most 2. So that's very restrictive. And we also, from that, kind of this every component thing kind of gives way to this part that we only get these critical graphs of largest possible order when the complement is connected, which means it's not the result of a join of smaller graphs, which is nice because if we have a critical graph that's the result of joins of smaller graphs, then each of those pieces has to be critical. So if we're trying to build up a complete list of k-critical graphs from 3, 4, 5, if we're trying to fill out 5 and we already know 3 and 4, and 2 and 1, I guess, but those are the same for everything, we already know which ones are the result of joins. It's just all possible ways we can combine them to get a 5 colorable graph or 5 critical graph there. So with that, our structural result here, we're able to use Brendan McKay's NAUTI, just use the GenG command or the gen command. I don't know how other people say that, or if there's a known convention on how to say that. We were able to generate all connected graphs that are triangle free of order at most 13. So connected is important and triangle free is important because we're going to take the complements of these. And since they're connected, we know when we take the complement, right, they have connected complements. And because they're triangle free, we know the independence number is at most 2. Then we just took that output into Sage and searched for all k-critical graphs for k less than or equal to 7. And that's where the real chugging started, right? NAUTI didn't take very long, but Sage took about 12 days on my desktop because there was about 18.5 million graphs to go through there. And each time, right, you need to do k-colorability, and k-colorability is slow in general, right? So it was about, 13 to the 7 every time. And then we were able to search through those, right, for critical graphs, and then find the smaller critical graphs by joining the smaller ones together, as I mentioned. And with that, we were able to fill out this table, right? So we have the upper bound on the order, and we were able to get the complete list, right? So I know this isn't the complete list of graphs. This is just the numbers of each, but there's just too many graphs to list on a slide here. So this was known for 4. We've got the complete list for 5 critical, P3 plus P1 free. So there's 178 of those. There's 18,006 critical, P3 plus P1 free. And then what really lagged the computation time is this 7 critical, right? So there's 6.3 million of those in general. So I guess one thing you might be thinking is, even though this algorithm exists, this is kind of impractical to run an algorithm by checking for 6.3 million graphs as an induced subgraph every time, right? So even though this is polynomial time, the constant is very, very large here. That's 6.3 million. Right, that's true. Also, right, this is to solve 6 coloring, so 6 to the n gets pretty big every time. So I don't know. probably no one's ever going to implement this algorithm, but I do have the graphs in G6 file on my computer if anyone ever comes knocking. But I will say this is nice because we saw one example of in the table the other table that I presented in this talk, right? We saw some examples where there was finitely many 4 critical, finitely many 5 critical, finitely many 6 critical, and then we saw finitely many k critical for all k. So this is the first result that I know of. There might be others out there, but I'm pretty sure this is the only result where we have the complete list of 7 critical graphs where we forbid a single subgraph and it's not trivial. So for example, excuse me, if we forbid P4, right, we only get complete graphs. So we have the complete list of 7 critical graphs is just the complete graph. But when it's not trivial, excuse me, this is the first example I know of. So that's another reason this is nice. But we've exhausted our, at least my computational abilities. I'm not going to be able to get 8 critical using the same methods here. So let's just talk about some open problems and then I'll be done here. So these are the 2 main open problems. I think these open problems are fascinating. I think any progress towards these is a big result. So this is to solve, for which graphs H can we forbid and get finitely many k critical for all k, right? From our results now and from Maria Chudnovsky and their co-authors' recent results, it has to be one of these 2 forms. P3 plus RP1 for some R greater than or equal to 2, or P4 plus SP1 for some S greater than or equal to 1, right? So if you can do something like we did and get this done for every value, even though we did it just for, the path here being 2, that would be very interesting. If you could even just get this for 2 and 3, or this one for 1 and 2, I think that would be a very interesting result. But kind of directly from our result, maybe something you want to work on with a student or something, those ones might be hard. Maybe you want to just see if you can further refine our results on P3 plus P1 free graphs to get a structural characterization of these k critical graphs, because just brute forcing them isn't going to work, right? We know the independence number is small. We know the other thing about if they're the result of a join, but is there a complete structural characterization there? And that would help generate the full list. And the other thing that could be done is, our proof, I already mentioned the upper bound on the order of these k critical P2 plus LP1 free graphs is huge. And we think really far from the truth, makes it too difficult to generate with computers for any reasonable value of k. So can anyone tighten that upper bound so that those can be generated? And that's that. Thank you very much for listening.
Thank you very much, Ben. That was a great talk. On behalf of myself and Danielle, and ARMS, we'd like to thank you for that.